Okay, so I'd like to thank you all for being here and to attend this special talk online. We are here to welcome Ching-Wei Wang. She's professor at National Taiwan University of Science and Technology, and she's going to give us a special talk of more or less 45-50 minutes on the title Deep Learning and Computational Pathology for Precision Medicine. She's also going to provide us information on the joint program between Polimi and the National University in Taiwan and the exchange program. So thank you once more, and the stage is yours.
Thank you, Marco. Thank you, Antonio. Yes, hi, I'm Ching-Wei Wang. So today I will just, in the first part of the presentation is about the scholarship part, the scholarship offered by the university for the master program and then also PhD program, and then also about introduction about my department, and then I will talk about deep learning. That's my expertise, deep learning in medical image analysis and computer vision. Yes. So that's me. Okay. So my research focus is mainly on yeah. My research focus is mainly on deep learning and machine learning, and also I build AI clouds in my university, and then also I did big data analysis because right now all the data we process on the digital pathology is one slide can be like, some slide can be 7 GB single slide, but some slide can be 1 GB, 2 GB, depends on the scanner and the size of the biopsy. Okay, so I did a lot of things on pathology AI and also cytology AI. So you will see my recent publication all on this area, but I also did a lot of things on medical image analysis and the computer vision and the image processing. And I noticed some people here, some scholars here may be working on surveillance data or automatic driving. That's also part of my research, but you won't see it in my publication record. You will see it in my YouTube channel, and you will see a lot of demonstration on my YouTube channel, a lot of things about automatic driving stuff. Yes, so I have YouTube and a GitHub. You're welcome to explore. Okay. My PhD is in Lincoln, UK, computer science, and my master degree is also in UK, Glasgow, and IT. Okay, so that's my university ranking. And that's the ranking as well. Okay, so my department right now mainly have several areas: AI, deep learning, and then biomaterial, biomedical, electronics, and information and biomechanics. So those are the 4 areas, and we have 7, going to be 8 professors in my department. So compared to the department here, probably small. Okay, yes. Okay, so that's me. I will. Okay, and apart from the like we have because I work on building AI system that's not just for 2D data, or sometimes for video and 3D data, and also for recently I got an award in 3D CT segmentation. That's to build a universal region segmentation model that's for all the region here from here to here. So the single model can detect all the region within 2 seconds. Okay, and then we won third place in an international challenge. So that's also one recent work I have done. And this is what I want for building AI cloud system. So I build an AI server node to compute everything. So this allows us to collaborate with the hospital. So I have a lot of hospital, local hospital, collaborate with them so they can dump their data, and we can immediately build AI system, and so the publication will be very, very fast. Yes. So these are just some, and there are some professors working on biomechanics as well. Some professors working on tissue, biomaterials. Okay, and this is the part probably students are more interested. So we are recruiting PhD and master students. And for PhD, please, you can also go to my website, and you have the information here. Basically, this is copied from my website. and you have the information about how to apply for PhD position and how to apply for master position. Make sure you apply to the right department. PhD is the applied science and technology, and master is for graduate institute of biomedical engineering. This must be correct, okay, to the correct department. But this is probably you need to check the latest website, and then they will have the latest information. Okay. And there are some, I believe you all fit for this one. Okay. Yeah. For European students, you don't have any problem about this one. So there's some English criteria. Okay. So this is the university scholarship. I will talk about other scholarship offered by Taiwan. So for master degree, you have a 12,000 for full, and then 9,000 for partial, and for doctorate degree, you have 18,000 for full, and the partial is this amount. But in addition to this one, you can get the
Oh, my bad.
Oh. Okay. In addition to this one, you can also get an STC scholarship, as I mentioned. Okay. This scholarship is much higher, it's 40,000 per month. So for PhD, so you might be able to get both, but both are competitive. And if you are interested, you definitely will come to send me your information and contact me. So for this NSTC scholarship is 40,000 NTD per month. Yes. So next I will talk about my research focus. It's mainly deep learning, medical image analysis, and computer vision. Okay. So why we need to build AI models, especially for precision oncology applications? The reason why is right now, although the cancer treatment can be promising, but only a small amount of the patient are beneficial for those treatment, because for some treatment it can have a positive response for certain patient, but it can have serious adverse reactions. So it can be bad for some people, but good for some people. Okay, so then patient selection is very important to select the patient which can get the right treatment. And in Taiwan, we have national insurance system. I don't know about system here. So the government will pay the patient to get the proper treatment if they are validated by a certain biomarker. Say, okay, you have a very high chance to get very good treatment response. Then you are qualified to get a treatment and get a support from the government. So that's why it's important to have a certain biomarker tests widely applied to the clinical application. Is that also the same here?
We have like state-based medical insurance. I'm not sure about qualification for treatments. It is works the same way, but generally speaking, if your doctor prescribes a treatment, the government then basically covers for it. We also have private options, but they are elective, so you can choose to do it if you have money, for example, but it's not necessary most of the time.
Okay, so you mean in Italy it's also the same. So the patient can say, I want to get this immunotherapy treatment.
Usually it would be the doctor that prescribes it for the patient, and then the patient can go and get
for free,
yeah.
or low cost.
Yeah.
Okay, but if the patient say, no matter what, I want that treatment, they pay by themselves.
Yeah, then they can pay for medicine.
So then it's probably the same. So then the patient have to do some examination, like, okay, you have, for example, BRCA positive, or you have PD-L1 positive, or you have something positive. This indicates you will have very good response for certain immunotherapy, and then the government say, okay, this patient is qualified, the medical doctor, they can prescribe this patient with this treatment. So that's why there is a need for clinical patients. Okay. However, okay, so in my recent publication on these two papers, okay, so we did a However, for some information for certain indicator or certain biomarker, it's very, very expensive, and then the procedure maybe not so robust. For example, the MSI, and also like microsatellite instability, and also tumor mutation burden. These are the two very popular indicators right now currently used to for patient selection in immunotherapy. Okay, but for example, for TMB, it's the elimination of this one is probably impossible to widely apply in clinical patient because it requires NGS. Okay, that's super expensive. But for MSI, usually people will use PCR or they use immunochemical staining for kind of immunochemical staining, and then to do the eliminations. So the goal is to build an NI that is effective, efficient, and low cost, and easily accessible in clinical applications. So we use histological slide, H&E slide. Just based on this slide, we try to predict the patient status of TMB and NSI. Okay, and then the reference standard we use is not manually because it cannot be manually analyzed. Those two status. Okay, like I say, you either have to use immunochemical staining to get the result, or you need to use NGS to get the real answer. So the reference standard we have in this study are NGS. So it's like 100%, not 100%, it's highly reliable. Okay, so in this study, we have collect two cohorts from two different cancer. One is endometrial cancer, the other one is colorectal cancer cohort. So make sure you want to test, does the model work robustly in two different types of cancer? And in the meantime, it can also do perform cancer subtyping, because in endometrial cancer, you can see there are different stage, G1, G2, grade 1, grade 2, serous carcinoma, and grade 3, and then hybrid 1, serous carcinoma. And in the colorectal cancer, you have mucinous, non-mucinous adenocarcinoma. So it's not just predicting the biomarker, it can also use to predict the subtype of the cancer. Okay, and those are some race distribution, age distribution, and then the data. So you can see this is for people working on small image, probably you don't understand how difficult this task is. This is the number of slides, the y-axis, and then the x-axis here shows the dense distribution of slides, and then you have width and height. Okay, so this many pixel in width, this many pixel in height. So that's why I say it can be 2 gigabyte per. Okay, so it's a huge slide, and then based on this information, probably a lot of it garbage information. Okay, and then no doctor can tell you which part is correlated to TMB or MSI. Okay, so that means you need to have a robust weakly supervised learning method that automatically learn what's the most important part, because no manual annotation are available. You only have slide level information. So what's the deal? The deep learning automatically identify the key information, automatically build all the patterns, and deal with unbalanced data set, deal with maybe noisy label or like real clinical data, and then try to find out whether it's possible to perform this task. Okay, and in this study, okay, so we also benchmark several SOTA methods, state-of-the-art models in computational pathology, mostly like Caminella. This classic MI is published in Natural Medicine, yes. And those my two previous work, Clan and Toad, one of it is published on Nature, the other one is published on Natural, I forgot, Natural Medicine or Natural Medicine. Okay, and this is MIA and some maybe MIA. Okay, medical imaging. Those are the recent work published in leading journal, and then we benchmark with them and then show that it's possible the method can be used to predict the biomarker, just use directly from histopathological side, which is routinely produced in clinical practice. So that means this work can be widely applied in clinical practice. And what's the model inside? Anyone here have anyone here heard about transformer? Can you raise your hand? How? Okay, how many of you use transformer? Oh, good. So we have three. Yeah, you want to raise? We have 3 people. So it's getting popular, right? Because people, it's effective. The training time is so fast. Yeah, that's a benefit of transformer. Okay, so we have a transformer-based ensemble model. The transformer is applied not just in the encoder part, but also in the classifier part. So we have transformer in both parts. Okay, so in this model, we have a self-supervised learning, and then the backbone is VIP16 large region transformer backbone. So anyone use self-supervised learning here? Oh, you again. Good. Okay, which self-supervised learning strategy do you use?
Basically, I'm trying to apply to the video segmentation pattern which we were talking about yesterday. I'm trying to reconstruct the input.
Yeah, which one? Because there are many different self-supervised learning strategy, like local V2 or VT or.
No, basically, I just give the input and try to reconstruct the input from that.
Okay. Yeah. And
Yeah, I'm using Dino.
Okay.
I was looking at your.
Me too.
A mix. I'm working on graphs. The strategy is basically the same.
Yeah. So the self-supervised learning strategy is also very useful, I think, because recently I found it's very useful. Okay, so the encoder, because you can see this huge dimension of the size, huge. You can think of this data, it's just like Google Map. You check your app, Google Map, you have a huge, large image. So this is large image. But in this large image, how do you throw away some garbage and then maybe how to encode? You generate some extract features effectively. So this is our self-supervised learning feature vision-based transformer feature encoder module. Okay, so and then I also have an ensemble model. In my work, I tend to use ensemble model because ensemble model is just like when you have a company, you have 10 smart people, 20 smart people, they can definitely make a good decision. Right? One smart people, sometimes I'm sleepy or I'm biased. Okay, so probably I don't make very robust, reliable decision. But ensemble model with proper model selection strategy, I found it's very useful to generate a good, reliable predictions. Okay, so this is the ensemble part. Okay, and also, anyone use multiple instance learning, MIO? No? Probably, if you work on classification system, anyone here work in classification system? Yeah. So what's your applications?
I mean, my work is on graphs, so I try to classify like the binding with the proteins, stuff like that. So I usually use pre-training, self-supervised with Dino, similar method, and then a simple classifier like linear networks.
And your application is a binary classification or multiple classification?
Usually binary.
Usually binary. Yeah. So this transformer transmitter, okay, transformer base. So basically, we also encode data, even it's because after we use this encoder, it's already become features. Okay, and then we have these features like put it into transformer MIL, okay, model, and then so this can be as a useful base classifier. Okay, so yeah. So and this is a model interpretability part because a lot of people think, okay, machine learning, deep learning, they are black box, but they are not because you are able to extract the attention mask of the model and then say, okay, because we teach them how to learn, we assign them learning strategy, learning behavior, but in fact they learn by themselves, right? So this is their model and then their attention, and then it is found that, okay, after extracting their attention map, and then we found the model does pay high attention on the tumor region. Even we didn't tell the model which part is tumor, which part is not tumor, okay? So, okay. And then we also analyze the runtime analysis because no matter it's in gigabyte medical image analysis or in computer vision, automatic driving, you also have a problem like, okay, I want it to be not just effective, but also fast. So here we analyze like 3 SSL methods like VT, MoCo, V2, SWA, Dino, okay. And then use different backbone, and then you can see, given a back file size 287 megabytes, and then the Dino with VIT method compared to ResNet 50, we have reduced the file size effectively, extract the feature just 18 MB. So this is very effective. And then we just show this method have a better efficacy as well. Okay, and then this is some runtime in feature extraction. So it can extract feature effective, but the runtime is not too slow. Okay, similar. And then the backbone, the runtime AI inference. So you can see the AI inference time is okay, right? And then the training time, and then this one. And we found because in digital pathology, the problem is because one slide is huge, and if you have many slides, a lot of method, the so-called method we test might take 2 weeks, 3 weeks just for finish the experiment. This one, I remember for training, it's just hours. So it's very fast if you want to say, I want to build that model. I don't want a model takes too much time. This is highly effective, and then also the data efficiency is very high because you can extract the feature effectively. Okay, and in the paper, you can check the paper because we also release the data and also code. Okay. So the second research I will mention, because a lot of people are now working on classification. So far, we only have 2 people working on classification, right? The rest will be working on detection, segmentation. Yes. Who? No? Who? Okay. yeah. How many people work on detection? Detection and segmentation. Detection? Yeah. 2. Who? Segmentation? 2, 3. Oh. What else? Okay. Yeah. So the first work I share with is about classification. Classifier. It can be used on many applications. Okay, and it's weakly supervised classification because it only requires slide level label or image level label. It doesn't need annotation inside. And this one is about detection and segmentation, cell-based segmentation. So the problem may not just happen in medical image analysis, but it also happen in industrial application like defect detection. They also have similar problems. Okay, so here we just give an example. So in this problem, we have 2 image modality. So you don't say I have a model which only can work on 1 image modality. You have 2 image modality. One is fluorescent image. The other one is light microscopy image. So, and the first problem, you have unclear and blurry borders. This also happens in computer vision data. Okay, so some is really blurry. Okay, and also the target object can be variation on the image appearance can be widely, can be different, very, very different. And also overlapping objects, so you have overlapping signal. And the last problem is the most terrible one. I think a lot of model will fail because this one. And our model tend to try to deal with this problem is sparse annotation. What's sparse annotation? Because sometimes human, when they, or medical doctors, when they try to annotate the data, they only annotate the object with high confidence. So they only annotate several ones. But the rest, they don't annotate. Okay, so you kind of confuse AI saying, sometimes this one is the target, but the rest is the background. So you confuse the AI. Sometimes it's yes, sometimes it's not. So this will totally confuse the AI. So the sparse annotation is a very big problem in especially in these applications. Okay, in medical image analysis. So we try to deal with all these problems and then generate segmentation model. Okay, and this one we have a 2 modality and a 2 cancer. Okay, because initially we only have this single cancer data with 2 image modality, but the reviewer asks us to extend the experiment to different kind of cancer, so we extend to this stomach cancer as well. Okay, and then okay, so and the model is like this, so it's a soft sampling, cascade deep learning approach. So basically, we have a soft sampling model to deal with the problem as well. So this will correlate with the usually we have soft sampling and then we also have soft labeling in a lot of work. Doesn't matter it's classification, segmentation, or detection. I usually have that one. Okay. And that's the after segmentation, it extract the 2 signal, and then you need to quantify based on the signal ratio. You need to quantify the HER2 expression level, and this one will guide whether the patient will be suitable for HER2 immunotherapy. Okay, and we also benchmark with various segmentation methods. This is the backbone information in the study. Okay, and these are some qualitative and quantitative result and the box plot of the result. Okay. Okay, and this work is about 3D, the universal lesion segmentation challenge I mentioned in the beginning of my talk. Okay, so traditional manual annotation may take about 30 to 60 minutes. Okay, so in this one, we build a model that takes only 2 seconds on local computer and 3 seconds on the brain transit platform, because they also need to have some overhead there. And that's the illustration on different lesion segmentation. So one single model can find all the lesions. Okay. And apart from the medical image analysis work, I also have a lot of work on automatic driving, Edge AI, byway AI. This part, currently writing a paper. Yes. Yeah. So yeah, but this you can see on my YouTube channel. So that's all about my presentation. Is there any question?
On the line? Can you hear me?
Exactly. We do have some people online. One of the yes was a PhD of mine previously, so that's why.
Yeah.
Go Isa.
Okay. So I'm Isabella. Nice to meet you. I'm a PhD from the lab and I'm mainly working on this stuff. I'm so sorry because I was a little bit late during the talk, but I'm pretty interested in the part of the segmentation work. And I have some question about that. So I've seen that you use like different kind of modalities during the segmentation, and I don't know, or didn't understand actually how did you manage to use two modalities for segmenting. The other stuff is, did you use just semantic segmentation for the HAR quantification, or did you explore, or do you have some plans also in like trying a panoptic segmentation task instead just the semantic, since the task is HER quantification that usually requires like counting cells and then like providing a score about the HER quantification?
For the HER2 quantification part, right now we have this qualitative analysis to extract this part is after serial segmentation, and I further have some stem extraction method that can directly extract. For example, this is the A is the raw image. We have some stem extraction method that is able to extract the information to this channel and this channel. Okay. And then based on those information, we can further identify this information are the CN17, and this information are HER2 and the partial CN17. So based on these two channel information, we will be able to compute the final, the red one and then green one. Green one is CN17 and red one is HER2. And clinical application is they have a ratio to divide the number of CN17 divided by HER2. Okay, but they only have several cells. So we have so many cells, and then we can calculate the ratio. But I kind of forgot in this study, do we? I remember we have, but I'm not quite. I forgot. In this study, do we do correlation analysis on the pathology score and the AI score? Do we do that? And do we generate evaluation result on the correlation analysis? I forgot, did we do that? Maybe not. Need to check the paper again. Yes. Yes. And your first question, I don't understand. Any translator? No? I didn't get the first question.
From Isabella.
Yes.
No.
No.
Lisa, can you repeat, please?
Yeah, the first question was about like how did you manage to like, so which kind of stain do you use for training the network?
We use both data to train.
Okay.
Yeah.
And like how did you manage like to like, because for different stains we know that like we have different kind of information within that, and like how did you manage to like tackle each kind of information for each modality, like fusing each modality, or early fusing, late fusing, or
Okay. So for the okay. So for currently it's one model for each.
okay.
Yeah.
Okay. Yeah,
So-
because like I was wondering, like since like each modality gives different kind of information, we have a lot of like multimodal models nowadays that are trying to merge different kind of information from different stains, and we know that like we have a lot of stuff going on with the fusion, early fusion and late fusion. So I was thinking about that. So thank you.
Thank you. Is there any question? Yes.
I've seen that you have worked on registration,
Yes.
which is quite tough. I'm not a computer vision guy, but we were working on registration. So, my question is, this is a very niche topic that not many knows, not many deal with. But you work deeply with deep learning and machine learning models. Do you think that there is still room to do something on that side, specifically for registration? Or
Yes.
what's your take on that?
Okay. Can I?
Yeah.
Is it possible I can go to my YouTube?
Yes, I think so.
That's another.
Yeah,
I see, so.
should be any browser.
Okay, like click anyone?
Yeah.
Okay. So,
Just accept the.
okay. So YouTube. Okay. What's that?
Yeah.
Need your permission. Okay. This is the gigabyte data. We do the registration as well.
Yeah.
Okay. So are you saying is there any more application require this one? Yes, in medical application there's many needs. Yes. So right now I have a new topic coming. Because before, like you say, registration is just a pre-processing approach. So it's not really linked to the application. So before I did a lot of registration work and then how to find out where is the clinical need I can apply to. But right now I found one new recently a doctor come to me and for drug discovery, they have something and then they think this can be critical for them. But of course, it's still a pre-processing part.
Yeah.
Okay, you align two things and then you can analyze things and then you can find, okay, where is the biomarker, which is the most influential gene, influential DNA. So it can be useful. Yes. Yes.
Interesting. Thank you.
Yes, and that's
That's
yes. So this one is built from my AI. So okay, this is just showing the image is so big, right?
Yeah.
So tumor have to draw, and then to find the tumor. Okay, so it takes without registration. It's based on this is HNE, this is IFC, the histochemical staining, and this is the conventional histopathological side, HNE side. So with this image, it's just a large Google map, hard to find where is the cancer. But if you have the slide, I slide and the HNE slide, you can have the marker there. And this one already tell you, okay, I try to use a image that's easy to show. For some image, it's really tiny. Okay, so this one already tell you this is the tumor part. So for human, it takes a long time to eat. Okay, but with registration, one click, then you find it. Okay, so this is we have this auto registration. One click. Remember, this is a gigabyte data. It's not small data. You can align the data and then you can directly find it. So that can be convenient. But of course, this is a pre-processing part. Yes.
Do you think that an accelerator for doing this task is?
So what?
Because we were working on accelerating that process, so designing architectures for that.
Oh.
And do you think that there is some utilities in that work that you were doing, having something that's even faster?
Yes, definitely. Yes.
Okay.
Yes. Like this one, I think I published in some paper already. So because it's gigabyte data.
Yeah.
So it's supposed to be slow, but we are able to make it very fast, and it's on a cloud, so it's on a server. It's not on a local machine.
Okay.
Yeah. So it needs to be fast and efficient. Otherwise, your memory will crash.
Yeah.
Yeah.
So roughly, like how much time does it take? So in terms of given the size of the data set, like how much time does it take to registration?
Like this one, I just showed you. Click.
So okay, so it's very fast.
Yes. Yes.
Okay. Yeah.
Mm-hmm. Yes. But if you are interested in more YouTube, like this is the bone marrow analysis. People are working on the, like this is the bone marrow slides. Okay, this slide, the scanner, based on the scanner, one side is really huge. I remember one side can be 60 gigabytes. Okay, and it can detect all kind of different cells. Yes, and then the seal looks very similar to each other. Yes. So yeah, so you're welcome to check. Yes. Thank you. Yes. You have any more questions, you're welcome to ask or you can again.
Since we have them, we can ask something about the experience.
Well,
does yes.
Oh yeah, share your experience. I'm writing a paper.
I know that you are not shy.
Yeah. I mean, we work here in Taiwan, and we are currently working on a paper for the detection and classification of the traffic sign recognition. And
Something about the experience.
Yeah, okay, about Taiwan. I think that it's a place that you do not usually consider to go to, even for studying. It's usually not the first choice of many students, mainly because it's not known, okay? So our experience was, I've been to Taiwan before, I liked it, and I wanted to go back. And like doing this experience all again allowed me to also appreciate more the university settings and how things are done, like in a very neat and organized manner, which is quite different from here. Both the culture you experience every day and the culture you experience in the university offer a very different perspective on things. And also courses and research. I think the whole university is very oriented to research, which is something that I found here at NECST Lab, but not in all university courses. So it's just a different approach. And if you have the time to go there or to do something, I'd say take it.
Also, I think it's way more practical. We had, like in professor's course, we had an initial part about just coding basics and some basics about computer vision. And then most of the course was like, do this project, learn to stuff and just try and see how it goes. And it was very helpful because I had never worked with computer vision and I learned a lot of stuff doing it. So I really like it, and it's way different from what we are used to doing in Taiwan University.
So if you are a Polimi student,
yeah,
doing your master here, what do you have to do in order to apply?
We did just as an Erasmus. It was an international mobility program, so you just go on the online services and go into the international mobility section, and you can apply for
also the visa process to go to Taiwan is pretty easy. We just have to go to Milan with an embassy, some kind of embassy, and not proper embassy, but similar.
consulate.
Yeah, consulate. Yeah, sorry. Yeah, that's pretty much it. After a 12-hour flight, you're there. Pretty easy.
Flight is long, but
How many courses did you take there?
6.
yeah.
Yeah.
Which is a lot for Taiwanese.
That's 3/4 of their master degree, because it's just 8 courses, but plus some labs and practical things, correct me if I'm wrong. And it's a lot to take 6 courses there, but like Polimi just consolidates. So I have to do good extra work.
When you say 6, and
Yes.
you're saying, it was kind of weird because it seems that, was it allowed or?
It is.
Okay.
You're right.
6,
Yeah, we want this.
Probably too large number for this kind of exchange programs,
We-
which are
we-
more related on research.
Yeah, we had a lot to work to do, also because the project all come together in the last 2 weeks. So we had to work on like 4 different projects all together. Yeah, I know it's a lot, but we didn't want to fall behind with the university schedule, also for graduation and stuff, so we had to.
And
You
yeah,
take
we had
also exams by remote here while you were there.
No, we followed some courses and then we took the exams once back because we finished the session on December because in Taiwan the semester is 4 months. And then you can, we just float back on the 23rd and then some, yeah.
So yeah, it's very useful because now we have all the exam session here and we have some exams back, so we can just take them. And it's very useful in that sense also.
I would say they are trained to work on.
Yeah, last weeks were very, very busy.
I know they work with.
We are trying to extend the exchange program also to include other master programs here, including biomedical engineering that at the moment is not. So we should be able to easily, I hope, to modify the agreement and then also biomedical engineering students can.
Thank you.
Question, curiosity? Also from online? So I think we can thank our speaker. I can stop the recording.